Hello again. Let's continue talking about chiral molecules, but today let's talk about how to name them, how to assign configuration. Okay, so we're working in Key Concepts, Unit 1, Part 6. The first page of that document looks like this. You have to scroll down a ways. On the screen, I cut out the stuff we've already covered in a previous video. I'm going to scroll down this part called Assigning Configuration. You know how you have to configure your computer when you get it set up? You have to set all the settings correctly. I guess that's what this term is referring to. We have a pair of chiral molecules like our left and right hand. They're incredibly alike. We want to assign different names to them. So we have to kind of pick out the configuration, the three-dimensional shape, of which one is which. This procedure to assign a new name, or at least a new prefix, to a given enantiomer is completely arbitrary. It was designed by three scientists, Cahn-Ingold-Prelog. The IUPAC committee said, we like it, we'll vote it in. And so this is our procedure. So you need to memorize the procedure. And I'll come back to the fact that it's pretty arbitrary. Save that for later. Okay, so what is this procedure? Okay, well, you're only going to use this, well, that's not true. You're mainly going to use this if you have a chiral molecule. So you first have to find the chirality center. That atom, which is usually carbon, attached to 4 different groups. Cool, that's what makes the molecule chiral. Find the chirality center and then look at the 4 groups and rank them. Okay, how are we going to rank them? We first rank them by the highest atomic number. So use the periodic table. So I got a portion of it down here. So carbon is element number 6. That's its atomic number. Oxygen's going to outrank carbon because it's element number 8. Iodine is number 53. So it's winning so far. It outranks everybody else. Hydrogen, first element, is going to be the lowest ranked group. It's going to lose just about every time. What happens if you have some ties? Okay, so if you have 2 different types of hydrogen, deuterium, we spoke about that in a previous video. Deuterium is hydrogen. It just happens to have a neutron in it. Protium is a name for hydrogen that does not have a neutron. And so if you have a tie, deuterium versus hydrogen, normal hydrogen, deuterium is going to win based on mass. That's your first tiebreaker. Another tiebreaker, well, that's not a tiebreaker, it's another circumstance. I mentioned in a previous video that we're going to deal mainly with carbon attached to 4 different groups, but other chiral molecules can possess other elements, other chirality centers that are not carbon, in which case they might have a lone pair. That might be their 4th group, a lone pair of electrons, in which case that has no protons, doesn't have an atomic number, so the lone pair of electrons is going to be ranked lowest. Okay, we're not going to really see that in introductory organic chemistry, but it's out there for the chemistry majors. Finally, we're going to break ties. This is very common. Let's say you have a carbon-carbon chain, and your chirality center is one of the carbons in the middle. So the 4 groups to that chirality center, 2 of those groups at least, are going to have carbons. And that's an immediate tie. You have a carbon on the left side and carbon on the right side. So how do we break that tie? You're going to go to the 2nd group of atoms, and you're moving away from the chirality center, and then rank those atoms and see if you can break a tie. The highest atomic number wins. If they're still tight, you go out a 3rd group of atoms and a 4th until you run out of atoms. And guess what? If it's still tied, you don't have a chirality center, right? You have to have 4 different groups. So there's got to be a difference somewhere. So you will find a difference. Highest atomic number is going to win. Okay, that takes the most work. You got a chirality center with 4 different groups. You get them ranked 1st, 2nd, 3rd, and 4th place. Once you do that, now we have to think 3-dimensionally. One's going to be a left hand, one's going to be a right hand. And so the way Cahn-Ingold-Prelog, the 3 scientists decided to do it, is like, well, take your molecule, bend it, twist it, rotate it, however, whatever you need to do, so that you look at the molecule such that the fourth rank group is away from you. Simply speaking, if you're drawing it, it's going to be on a dash bond. So I got an example over here, right? So here's a, well, let's not do this one. I want to do chlorine first. Go up above here. So I'm getting ahead of myself. Let's finish the rules. The name of the game here. So find the Chiral center, rank those four groups based on atomic number, breaking ties by going out to the next set of atoms. Then you look at the molecules in such a manner that the fourth group's away from you. So what I mean is, in this drawing, the hydrogen's on a dash bond, that's going away from you. So hopefully the hydrogen is the last place group, fourth ranked. It is actually, so that's kind of nice. So this drawing is set up correctly for step 3. The fourth rank group, hydrogen in this case, is going away from us. Next, step 4. You have to look at the first 3 groups. So let's just read it. Decide if the top 3 ranked groups are arranged clockwise or counterclockwise. Okay, so if you happen to draw the molecule like up here in the top left, the fourth ranked group is pointing straight up. So then you have to redraw it, or if you use your imagination, visualize this so that you're looking down below, upwards, such that the fourth ranked group is on a dash bond. Or redraw it. I know, that can be a little tricky, but we'll get more practice. And the more you practice, the more comfortable you'll become. Once you're looking at this structure in the bottom left, the fourth group is away. Now you ignore it. And you say, where's groups 1, 2, and 3? Well, group 1's on the bottom. Group 2 is on the top left. Group 3 is on top right. And so the arrangement is 1 to 2 to 3, 1 to 2 to 3. And if you go around the molecule in the 1, 2, 3 fashion, that would be like turning your steering wheel clockwise. And which way is your car going to turn if you turn the steering wheel clockwise? It turns to the right. Yes, so that's how it's going to turn to the right. So that's the way it's going to work. And then R stands for right. Technically, it's the Latin word rectus for right. However, if you look at a molecule and you put the fourth group away, like in the bottom right, this drawing down here is a fourth rank group away. Now look at the arrangements, 1, then 2, then 3, 1 to 2 to 3, 1 to 2 to 3, 1 to 2 to 3. They're set up in a counterclockwise rotation. And if you turn your steering wheel counterclockwise, you go to the left. So we're going to label this compound with an S. S is Latin derived from sinister for left. That's how it works. So we have R and S. You just have to remember, right turn and R makes sense. You have to remember that S is the notation for left-hand turn. And so I got a little story my chemistry instructors shared with me years ago. They said, well, back in the Wild Wild West, you know, the cowboys are carrying their 6-shooters, little pistols in their holsters here. And, you know, you walk up to a stranger and say, howdy, stranger. And the other guy with the black hat, uh-oh, he might be the bad guy. I'll be the bad guy. They'll say, howdy, nice to meet you. And he extends his right hand, and you would take it and shake hands. The bad guy would hold on to your shooting hand and draw his gun with his left and shoot you because he was sinister. Yeah, it's kind of a silly story, but it sticks with me and it helps me remember, yeah, that's right, S, left-handed, and sinister. All right, let's play this game, the naming game, the assigning configuration game. So over here on the right, I have a molecule with a chlorine. And if I say, hey, I need you to name it, then let's go above. There's the other drawing. So let's mark up this one. So the full name is required on my exams. And you'll say, okay, go back to the video about IUPAC names. And you'll say, okay, step 1, if we have to name it, is to find the longest chain or ring with the most important functional group. Come on, close it up. There we go. So it's a chain of 4. That's kind of nice. It's a nice straight chain. So here's the parent chain. Step 2 is to name it. Mabel eats peanut butter. Butter is the 4th word. 4 carbon starts with BUT. This is butane. This is the parent chain. Step 3 is a number to chain such that you get to your branches, your extra groups, as fast as you can. So don't come in here from the right, because this could have been 1, then 2, then 3. Nope, not chlorine on 3, but lowest number. Get your golf score down. It's 1, then 2, then 3, then 4. So then on carbon 2, there's a chlorine group. So we numbered a chain. Now step 3. Steps 4 and 5 is a name and number. I kind of already did that, right? So the name of a chlorine is chloro. The position is on carbon 2. And then to give the full name, you stick the prefixes up in front alphabetically. Well, just 2-chlorobutane. And we're done. At least I thought we were, back based on the video on IUPAC names. But it turns out we have a chirality center. And you could tell or suspect there's a chirality center and that this molecule is chiral because of the dash and wedge bonds, right? So normally 2-chlorobutane might be drawn like this, in which case we're done. This is 2-chlorobutane. We have no information, any additional information. I don't know whether this is one enantiomer or another. I have to assume it's a mixture of both, because I don't know if the chlorine's coming towards us or going away. But in the drawing on the right, the chlorine's coming towards us. So is this second carbon of the chain a chirality center? We go back to our previous video and say, well, there should be 4 different groups if it's a chirality center. So this carbon has an H, a Cl has a methyl, and it has an ethyl group. So yes, those are 4 different groups attached to carbon 2. This is a chirality center. If you have a wedge, you could also have a dash. So it turns out there's 2 forms of 2-chlorobutane, chlorine towards us and chlorine away. They're not the same molecules, right? We viewed the last video about chirality and you'll discover, wait, one's sort of like a left hand, the other one's sort of like a right hand. Really, really similar to each other, but they're different. Different molecules, different isomers. So they need different names. So here's our procedure. Step 1, to give it a different name. Here's our procedure. Step 1, find the chirality center. Well, we kind of already did that. It's carbon 2. This is the carbon with 4 different groups. Step 2, rank those 4 groups by their atomic number. Okay, so take a peek at the periodic table. What are we looking for? Well, the 4 groups on this chirality center is a hydrogen, a chlorine, a methyl. The first atom is a carbon, and an ethyl group, and the first atom here is also a carbon. So we want C, the carbon, chlorine, and hydrogen. Well, here's chlorine, it's element 17. That's going to beat out carbon number 6, and hydrogen's on the left side of the periodic table, element number 1. It loses. Sorry, hydrogen. You take 4th place because you're element number 1. Chlorine, you got first because you're element number 17. Highest atomic number wins. And then carbon, this carbon is tied with this one as element number 6. Okay, we don't have deuterium, we don't have lone pair. Here we go. How do we break those ties? Break the tie by comparing the second group of atoms away from the chirality center. Again, the highest atomic number wins. Okay, so looking at the methyl group, what are the next set of atoms? This carbon has a hydrogen, and a hydrogen. It's got 3 H's. That's what this carbon possesses, moving away from the chirality center. The other carbon, again, moving away. Well, the end of this line is a carbon, and then there's the unwritten H and a second unwritten H. This carbon on the right has an H, H, and a C. I like to think that maybe now they're suddenly playing poker and high card wins. So this carbon, that carbon wearing their hoisters and the black hats. And this carbon on the left is going to play its highest card. Not looking too good. Highest card is a hydrogen. That's atomic number 1. That's going to lose. Carbon on the right is going to play its highest card, a carbon, element number 6. 6 beats a 1. This one just broke the tie and just won second place. The other carbon has to take third place. And now we have them ranked. It's kind of all written up over there. We've got 4th place, 1st place, 3rd place, and 2nd place. Okay, step 2, ranking the groups. We just finished. Next, visualize the molecule with the 4th rank group on the dash bond, going away from you. Yay! This molecule is already drawn correctly. We're looking at the chirality center with the 4th rank group dashing, fading into the distance away from us. Perfect. Now look at how the rank groups are ordered. It goes 1 to 2, then the 3. 1 to 2, the 2 to 3, then 3 to 1. That is a clockwise arrangement. Steering wheel, if I turn it, it's going to turn to the right. So yeah, this is the R enantiomer. We would assign the R configuration. So usually it's enclosed in parentheses. And then we stick that right in front of the name. More properly speaking, you have to identify which chirality center possesses the R. It's carbon number 2. So the full name would be 2R. Carbon 2 is the R configuration, right-handed rotation of its 3 highest rank groups. And then the full name is 2R, 2-chloro-butane. That's the full name. That'll get you full credit. Now, it turns out, if you just give me this name here, R, 2-chlorobutane, that also gets full credit because there's only one chirality center in the molecule. So this R means chirality center in the R configuration. Well, if I draw the molecule 2-chlorobutane, I will discover carbon 2 is the chirality center. That's the one that's R. So then it's acceptable. IUPAC voted. IUPAC said, okay, it's all right to drop the number 2. But if you have more than one chirality center, then you have to include that number to identify which carbon has R, which one has S, and so forth. Cool. Do I have anything else over here? Oh, pretty much saying the whole thing. There we go. Proper name, acceptable name. It's okay. If that's the one and only chirality center, you can leave off the number in front of the R. All right, let's try it again. Let's do this molecule down here. So let's first name it by the IUPAC set of rules. Longest chain is 4 carbons again. Step 2 is to name it. 4 carbons is butane. Number the chain. Yeah, coming in from the left side to get to the fluorine as fast as you can. So this is going to be 1, 2, 3, 4. And then now the name of this compound. I'll name and number the substituents, the branches. That's a 2-fluoro. Don't know why I capitalized the F. 2-fluorobutane. I think I'm done, but why is this wedge bond here in the dash? Because there's a chirality center. So I need to assign the configuration. Okay, I'm gonna redraw this because I'm afraid I might mess up and think the numbering of the chain, I might forget that that's numbering the chain and get confused with ranking of the groups. Okay, so here's my chirality center. Go back to the procedure real quick. That's step 1. Find the chirality center. Step 2 is to rank it. Step 3 is to look out with the lowest group away, 4th rank group away, and then decide if it's clockwise or counterclockwise. All right. Groups again, starting with the hydrogen, the loser. Sorry, hydrogen. You're ranked 4th. Element number 1 is going to lose to element number 9, I believe. You get a periodic table on my exams. Yep. Fluorine down here is element 9. That's going to be carbon, who's 6. Oh, I'm scrolling that way. Just go up. Okay. And so again, we're going to have a tie between the methyl carbon and the ethyl carbon. So this carbon is element 6. This carbon is element 6. Fluorine's element 9. That took first place. This carbon and that carbon's tied. Break the tie by going to the next set of atoms. And after a while, you'll see the pattern. And you don't have to draw in all your H's. You'll realize, hey, this carbon on the right actually has a letter C here. Whereas this carbon's the end of the chain. It only has 3 hydrogens, which is the lowest rank group. This one carbon's going to outrank these 3 and break the tie. This carbon takes the next position. It's right after first, so it's second. This carbon takes 3rd place. Ranking done. Step 3, let's make sure it's oriented the right way. Yep. 4th rank group is away. Good. Now we can trust our rotation. Start with 1st rank, go to 2nd rank, go to 3rd, 1st to 2nd, to 3rd, like the 1st. Now you're not physically moving these groups, you're just seeing where they are. I have to move my pen from 1 to 2nd to 3rd to 1 to 2nd to 3rd, and I'm making a left-handed sinister move, left-handed. That's not L, that's S. This is the S configuration. I know it's kind of redundant, but what I wanted to do is just prove to you that wedge doesn't mean always R. Up here, the wedge bond was an R. Down here, the wedge bond's an S. Okay, so you always have to go through the procedure, no shortcuts, sorry. Here's another troublesome bit. Can you draw for me R2-fluorobutane? Okay, so that could be an exam question. The real exam won't have R2-fluorobutane. It might be S3-chlorohexane, right? Some other variation. So how you do it? I would begin by drawing it backwards. Sorry, read the name backwards. Start at butane. 1, 2, 3, 4. And then someone else might zigzag it this way. 4. And I'll do it 2 ways, just to compare and contrast. On carbon 2 is a fluorine. Okay, so if I decide to count from the left side, this will be carbon 2. I'm getting ready to attach the fluorine to this carbon, number 2. If I do it this way, zigzagging down to start with, this would be carbon 2. I'm getting ready to attach a fluorine there. I got 2-fluorobutane so far. I just need to make it R. Okay, so the methyl, ethyl, fluorine are my 3 highest ranked groups, just looking up above. Hydrogen, I'd like it to be away, which means the fluorine should be towards us. And this is first. Just looking up here, ethyl was second, methyl was third, and yes, 1, 2, 3, 4. So I guessed correctly. Yay! So it's got to be a wedge, right? Wait, this is first, second, third. Fluorine is first. Yep, beats out the carbon. The ethyl broke the tie over the methyl. So 1, then 2, then 3. Wait, this is a left-handed turn of my steering wheel. This is S. Oops. I wanted R. So You got a 50-50 shot anytime you draw a chiral molecule, right? It's either wedge or it's dash. Dash. It's not wedge. So the correct answer is dash. The fluorine must be away. This is the S enantiomer. Sorry. This one was S. We just proved it. Start with fluorine. Go to ethyl, methyl. That the way I drew it, this molecule here in the bottom right, that is the S enantiomer. A quick fix is just change the wedge to a dash. Let's talk about that a little bit more. Okay, so how come that works? There's a couple ways we can prove this to ourselves. One is just to draw in all the groups. If the fluorine is away, and this is a tetrahedral sp3 hybridized carbon, one group's away, the other group's towards us. So the hydrogen has to be on the wedge. This is our third place. This is our second place. This is our first place. This is fourth. And looking here, just at the rotation or the orientation, we got first place, the second, the third. It looks like counterclockwise S, but step 3 was broken. Step 3 is make sure you look at the molecule with the lowest rank group away from you. So some of you might be able to do this. Have you ever gotten on, changed a fuse in your fuse box of your car? For some cars, the fuse box is right next to the gas pedal on the side of the wall, next to the brake pedal rather. So you actually have to lay down on the floor of your car and go after the fuse box, in which case your head is by the brake pedal and the gas pedal. So imagine yourself lying on the floor of your car looking at your forehead, and there's the brake pedal and the gas pedal right there, and you keep looking up, you can see the steering wheel. Okay, that's where we are right now when we look at this molecule. And if I go 1 to 2 to 3 as I lay on the floor of the car, so if I get my son in there and say, hey, turn the steering wheel this way, don't put the car in ignition and drive, but the wheels will turn to the right. Okay, a lot of you don't get that. I understand. So let's do something else. So if you're looking at wrong, it's backwards. That's the main point. Fourth group turned out to be towards us. So whatever we think it should be, looks S to me. Well, the fourth group's not away. So it's not S. Flip it, it's R. Here's another idea. I got a molecule here. Let's hold up to the camera. Do I have it drawn the right way? No. So let's make the fluorine, that's coming towards you, but on the screen, the fluorine's away. So I need to flip it. There we go. Okay. Maybe. Let's check. So how's the chain zigzagging? It starts here up high, then goes down low. And on the screen, that's what we do. We start high and we go down low. Okay, so my chain is zigzagging correctly as the model. On carbon 2, yep, second carbon, the fluorine is away from you. This hydrogen is towards you. This hydrogen's on the wedge, just like on the screen. Excellent. Okay. So now, as you're looking at this, you're saying, okay, fourth group is fluorine, ethyl is second group, then methyl. That's going this way. Get my hand out of the way. There we go. Go this way. First group, second group, third group, first group, second group, third group, first, second, third, first, second. Okay, so my hand is now moving counterclockwise. That looks like it's S to U. But the whole time, is that right? I'm getting backwards on the screen. There you go, that's better. Okay, the whole time, my hand is moving clockwise when the fourth group, the hydrogen, is away. That's not working so well, is it? Let's get out of the share screen. Maybe we can do a little bit better. Okay, so we were looking at it this way. Get my face out of the way. Yep, zigzagging correctly. This is up high, then carbon 2 is down low, and the fluorine is away. This hydrogen is toward. Fluorine ranked first, ethyl ranked 2, then methyl. So 1, then 2, then 3. 1 to 2 to 3. So right now my stream, 1, 2, 3. My hand looks like it's going counterclockwise. I'm trying to spin around. And now as you're looking at the molecule, you actually see my hand going clockwise because I'm on the other side of the molecule now, as I should be. The hydrogen's going away from us. You're not going to have a model on the exam, but it helps get the concept in your head that if you're looking at the molecule, change your answer. That's all you have to do. Looking at the model, the drawing of the molecule incorrectly, fourth group towards us, you're looking at it wrong. You're supposed to have fourth group away. Fourth group is towards us. This is the wrong answer. It looks like it's 1 to 2 to 3. It looks like the left hand, an S configuration. The fourth group's not away. This is the wrong answer. It must be the other answer, not S, but R. Okay. I hesitate to show you this, but I better show you now so that some of you who, so that no one does this on the exam. How's this come about? Let's do this. So the question is, draw R, let me read it correctly, R2-fluorobutane, and the student drew this one here. Oh, that's the wrong one. You have to draw this one. This is the S. Let's start again so I can get it straight. Okay, the question is, draw R2-fluorobutane, and someone said, okay, here's butane, cool. Here's carbon 2, nice. Fluorine is going to be attached to this, and then the other group of this chiral center is a hydrogen. Oh yeah, but step 3 says it has to be going away. So I'm going to choose the hydrogen to go away and the fluorine towards us. This is all good so far. Awesome. Now let's check. I got a 50-50 chance. Did I draw S or did I draw R? Well, go to the periodic table, rank your atoms. Fluorine, element 9, beats out carbon, element 6, which are tied here. This carbon has a carbon. This one only has hydrogen. So this one took second place. Here's third. And hydrogen, you lose. You're the first element. The lowest atomic number loses. So first, the second, the third. Oh, man, I drew the S. So I need to flip it. To flip it means, change it, I should say. Wherever you had a wedge, make it a dash. Wherever you had the dash, make it a wedge. That's how you do it. Just do it that way. And automatically, this is going to be R. Because we checked that the other configuration, fluorine on wedge, is S. So if I switch the wedge and the dash, that automatically makes the other enantiomer, R. Don't do this. I've had students say, you know what, if I squeeze this fluorine up here, don't do this, don't do this. Why am I even showing you this? Someone will say, well, look, this is first, this is second, this is third. It's 1, 2, 3, 1, 2, 3. It's right now. Yay, I win. And I'll go, what's the difference between this drawing and this drawing? All you've done is twisted it. You put it into a new shape. The fluorine's towards us. The fluorine's towards us. You didn't change the configuration. You don't have the other isomer. You have the same molecule. So that's very much like saying, okay, here's the hydrogen going away, fluorine, but I don't want the fluorine here. I just want to squeeze it up to here. Now it's above. I didn't break any bonds. I'm just bending in this molecule into a new shape. It's the same molecule. Aye. So look out for that. You can't just move it, bend the bond. It doesn't change the molecule. I'm not changing the molecule. I'm just bending it. This is the same thing, whether I push this up here or leave it alone down there. Okay, so that's going to get you incorrect answers. So what you want to do is just make sure to spread things out. Bonds are made of electrons, and electrons repel. So I personally don't like this drawing on the far right because look how crowded this fluorine, this bond, the wedge bond, this bond over here. There's so much room down here. Why don't you spread things out? Yeah, this is just a bad drawing. Don't draw it that way because it can lead to errors. Did I harp on that too long? Sorry, pet peeve. Let's see. Let's try this one. A little more complicated. You might recognize this as Carbone. Ooh, is this the spearmint flavor or the caraway seed flavor, the rye bread flavor? You'd have to go back to the video and check it out. But I think the R Carbone was spearmint and the S Carbone was caraway seed or rye bread. So let's see which odor we have here. So assign a configuration, find out if this is the R enantiomer or the S. Okay, first, step one, find the chirality center. So we're looking for X's and Y's, intersection of 3 lines. Maybe that's a chirality center. No, this carbon's twice bonded to the same group. The chirality center needs 4 different groups. That's not a chirality center. The methyl here has 3 H's that are identical. It doesn't have 4 different groups. This double bonded O, the oxygen is not chiral. It doesn't have 4 different groups. This carbon has an oxygen, top of the ring, bottom of the ring. It only has 3 groups, not chiral. So that's kind of cool. When finding chirality centers, you have to have 4 single bonds to have 4 different groups. So that's not chirality center because that's a double bond. That's not chirality center. That's not. This is just a bend of the chain. There's 2 H's here. That's not, nor is that one. End of the chain, nope, 3 H's over there. Process elimination. Maybe, just maybe, it's this one. Where are the 4 groups? Well, on this dashed line is this group. On the left-hand side, I have all of this stuff. And on this bond, I got the right side of the ring. I don't know how far you want to go, but you can see that the ring goes up CH2, CH2, then it goes C double bond C, and then C double bond O. Ooh, the left side and the right side are different. This counts as 3 different groups so far. Wait, I need 4 different groups. The unwritten hydrogen. Right, skeletal drawings, you don't have to put in your H's. But carbon bonds 4 times. So where's the 4th bond? To the H, dash or wedge. I already have a dash bond, so this must be a wedged bond. This carbon's tetrahedral, sp3, tetrahedral. Going this way, you have 2 normal lines in the plane of the screen. You have 1 bond towards you, wedge, and you have another bond away, dash. Okay, step 1 done, found the chirality center. Step 2, now we have to rank them. So now we got, let's just start again over here. And we have to rank them, right. So 1 atom at a time. So starting at the chirality center, we have an H, we have a C, C, and a C. 3-way tie. But hydrogen loses to all 3 and takes 4th place. Okay, now moving away from the chirality center, for every carbon, find 3 more atoms. Well, this carbon over here has a C up here, and has a C up here, and 2 H's. So this C has a C, H, and an H. This C, this carbon is tied with that carbon. If you go up, it's a carbon. It also has two H's attached to it. So right now, these two carbons on the ring are tied. Darn it. But if you go down here, okay, this carbon, which is tied with the other two carbons, you go out to the left, you see a C. You go out to the right, you see a C, but it's attached twice. So you double count the C. So this carbon is attached to C over here, and this C twice. It must have 3 atoms to play the game. Now these 3 carbons are all tied. They sit down at the poker table and play their highest card. Okay, so this carbon plays down a carbon. This carbon says, okay, here's my high card. This carbon says, yeah, here's my high card. It's a 3-way tie. So they pull out their next card. Well, this carbon pulls out an H, an H. This one pulls out the carbon and wins first place. This carbon with the double bonded C beat out the single bonded Cs. So now we have a first place and a fourth place. These 2 carbons are still tied, right? So they play their 3rd card. And if they were different, then maybe we could have broken the tie, if they weren't. So now you have to go to the next carbon and have another tiebreaker. This carbon, let's do it over here. This carbon versus this carbon in the last tiebreaker. Okay, moving away from the chirality center, this carbon's attached twice to O and once to this C. This carbon is attached twice to C and once to H. Play your highest card. This carbon plays down the oxygen, element 8, and that beats out this high card, element 6. So this one just captured the next ranked position, which is 2nd place. And this one's 3rd. Should have drawn this 4 times on the screen. Okay, next. We got first place here. A hydrogen on the wedge. Ooh, that's nasty. It's 4th place. This one was 2nd place, and this side was 3rd place. Step 3 is look at the molecules such that your 4th group is away. This is drawn towards. We're going to get the wrong answer, but we just have to switch it. So step 3, 4th group should have been away. It's towards us. Change our answer after we get it. So what is the incorrect answer? Well, it looks like it's what? Well, looks like I lost the page. I'll go this way. Sorry. There we go. We're back. It looks like it goes from 1 to 2 to 3. 1 to 2 to 3. It looks like it's a right-handed turn, right? So 1 to 2 to 3, back to 1. It looks like it's R. That would only be true if the 4th group was away on the wedge bond. So the correct answer is S. And I think if we look up S caraway, S carbone, I think this is the caraway seed, the right flavor. Cool. Alrighty, I think that's, I'm not so sure. Is there one more topic? Yep, just a little warning. Back to optical rotation, right? So we got a molecule here that rotates plane polarized light with a negative sense. That means counterclockwise light rotation. Okay, and then Cahn-Ingold-Prelog, if you look at it, it looks like it's also S. What is S? It's a little misleading, because here's another chiral molecule. You put this molecule in the polarimeter, and it rotates light clockwise. But if you do the Cahn-Ingold-Prelog rules, the orientation of the priority groups is counterclockwise. It's S. So S plus, S minus. The point is, Cahn-Ingold-Prelog is an arbitrary set of rules that works for us and enables us to get a name, R and S, but they do not correspond to clockwise and counterclockwise rotation in the perimeter. They don't correspond to each other. So no shortcut there. Like if I said, hey, this is, this rotates plane polarized light in a negative sense, you can't immediately say, well, then it must be S, because that's not true. Here's an S enantiomer that's rotating it clockwise. Darn it. Okay. If you have questions, catch me on the discussion board or send me email. Take care.